Hello and welcome to our webinar today. I'm very pleased to introduce two of my colleagues who will be our main presenters today. The main speaker today will be Dr. Peter Hunt, who is our Director of Computational Chemistry. Peter has a PhD from Imperial College and probably won't want me to say this, but many years of experience working in the pharma industry, most latterly here in the UK working for Novartis, and then joining us about 5 years ago to take up control of our computational chemistry team and lead our research. We're also joined by Dr. Tamsin Mansley. Tamsin is our head of North America operations. Tamsin also has a PhD from the University of East Anglia. She's got many years of experience as a medicinal chemistry, including such pharma companies as UCB, before she sort of transitioned over to software, where she was an application scientist with a number of organizations, including OpenEye, and also joined the Optibrium team about 5 years ago when she became our head of North America operations. So making sure that all of our clients and colleagues out in the United States are well looked after. So as John introduced, today's webinar is about the new modeling capability that we've introduced into StarDrop 6.6. And Peter is going to guide us through some of the technology behind these models and the applications of those. So I'd like to hand over at this point to Peter.
Thank you very much indeed, Nick. Hello, everyone. Thank you for taking the time today, wherever and whenever you may be listening to this webinar. What I wanted to do is to describe the basis of the pKa model and its development, and the lessons that we've learned in the development of that model, which will help shape some future improvements. And as Nick says, this model is now available in the latest release of StarDrop 6.6. So I'll start off really with just a very brief introduction to pKa and then concentrate on our approach. So I like to think about pKa really as a proton popularity contrast between the solvent and the compound. And you can see on the slide the equilibrium that is there in terms of where that proton likes to reside given a particular pH of the solvent. Now, in our particular case, we are interested in that solvent being water. And as temperature can matter in this, we have tried to collate data that is only in water, not in mixed solvents, and at temperatures that are around about room temperature. Ionic strength does play a part in influencing pKa, but unfortunately, I have to say a lot of the references and a lot of the data that we collect don't actually specify ionic strength. So that's an unfortunate consequence of the data that's around. And so it's interesting to me to think that this is the smallest element around, hydrogen moving, but it's tying up a pair of electrons, and that influence on charge has such a dramatic influence on the properties of the molecule concerned. And it's really those properties from the molecule as how it interacts with its surroundings. So these are the binding to a particular target or anti-target protein. It could be, as we've described, its interaction with the solvent that's around it and the solubility that's there. It could be its interaction with itself. The crystallinity, the packing of a molecule would be dependent upon its charge state. And again, if we're thinking about in vivo experiments, you're looking at a distribution between lipid phases, oleaginous phases, and water. And the charge will have an influence on that distribution. So the ability to predict the likely charge state of a molecule can help with, in the design process, which is where we tend to be focused with StarDrop, on molecular similarity. Is a particular compound that you're designing likely to be equally basic as one you know the properties of? is a particular compound actually going to be suitably developable, because it is going to form a nice stable salt and not necessarily disproportionate. And if you have a prediction for pKa and able to look at the charge states of the molecules, you can use that as a descriptor in other models. Solubility, log D, affinity, those are just some of the in the list. And as I have actually been using our pKa predictions for solubility and log D modeling. And last but certainly not least, just some chemical synthesis planning. If you happen to know the basicities, what charge states you're dealing with your molecules, you'll know how well they are going to react. And so, considering that it is that pair of electrons that are important, what is it that our approach to pKa in terms of how we assess those electron distributions? Our model is very simple. It deals with three sets of atoms: the hydrogen that will be lost or gained from the solvent. X is a heteroatom, and in this particular case we have it as nitrogen, oxygen, or sulfur. And then R are the heavy atoms that are connected to that heteroatom. Now obviously, depending on the heteroatom and its environment, that number of R groups will change, and therefore what we have found is that the best way to describe that neighborhood is in fact taking the quantum mechanical descriptors that we calculate and averaging them over the N heavy atoms that are connected to X. Now I say we've used quantum mechanical descriptors. We have a QSAR built upon those descriptors, but we have to generate, and we wish to generate, quantum mechanical descriptors because they give us a more realistic estimate and evaluation of that electronic distribution, not only for the site that we're interested in, but how that site relates to the context of the whole molecule. And so you listed here, we have quantum mechanics for the polarizabilities, delocalizabilities of these atoms, bond lengths between them, and charges associated with these atoms. And we consider both the conjugate acid form and the conjugate base form. So the data set that we have created is a couple of thousand carefully curated literature pKa values, as I say, in water. And these represent 2,243 unique compounds that are either monoprotic or diprotic. And those diprotic compounds can be diacids, or they can be dibases, or they can be zwitterions. And the reason that I put carefully curated in there is because of the way that we've built this model, which is very atom-centric. We need to know with confidence which atom is actually losing or gaining the proton. And you will see data sets out there, even in north of the 10,000 data points. But in my particular opinion, having looked at a lot of literature data out there, the uncertainty that is associated with those data points and the atom sites concerned is just going to introduce noise. And so what we have done is limit our data set down to this approximately 2,500 values, just so that we have the confidence in the atom assignments that we put in. And so the data set, as you can see listed in the histograms, we have split that into a training set, a validation set, and a test set. And we have these three splits in a 70, 15, 15%, essentially so that we can build a model with a variety of QSAR and statistical methods. We use the validation set then to assess which of these methods is performing well. And then we test again. We test the model against a separate test set just to make certain that we haven't got lucky. We haven't just by a random chance managed to find a good performing model. So this is the predictive success of the model. I'm showing the points here in the validation and the test sets, validation in blue and the test in green. I'm also showing 3 lines on this graph. The line of equivalence is the middle, plus or minus 1 log unit of error from that line. And you can see that the vast majority of the test and validation points lie within those railroad lines of 1 log unit. On the right-hand side, I have the various methodologies that we've chosen. RBF stands for radial basis function. And this performs better than the random forests, PLS, and in Gaussian processes, which are listed in the table. Not only on the coefficient of determination, R squared, how those points compare to that line of equivalence, identity line, and also the root mean squared errors. So for the validation set and the test set, we are looking at very good correlations, or at least lying along the line of equivalence of 0.9, and the errors are around or below the 1 log unit estimate. Another way of actually thinking about how successful this model happens to be could be looking at the distribution of those errors, or the absolute errors as shown in these graphs, and how that varies, because root mean squared errors can vary and can be influenced by a few high outliers. So really, just to give you a slightly different view of how this model is performing, here is the distribution of those absolute deviations from the identity line. What one can see, if you concentrate on the far left-hand side, the 2 bars there corresponding to a deviation of 0.2 log units, we're looking at a third of the set, either in validation or in the test set. A third of compounds are predicted within 0.2 log units. If one goes out to 0.6 log units, then we're looking at 2/3 of the set. And if one goes out to 1.6 in the validation set, or even below 1.5 in the test set, we are predicting over 90% of those compounds in those sets. And so this particular model doesn't seem to have a bias in terms of we're not predicting bases better than acids. We are very equivalent in this, because this is a simple model which is not looking at a particular functional group. We haven't developed a model for acids and then developed a model for phenols and a model for bases. This is just looking at the single atom environment and treating it as that environment, not as a functional group. And so this model seems to generalize and perform very well. So if I may use a very bad pun in terms of the real acid test for any pKa, is how you can actually predict compounds that are outside of the sets that you've been dealing with. This should be an unbiased evaluation. And indeed, these are 2 references that have come out in the last couple of years. Sample 6 is a prediction challenge, and very fortunately in 2018 they had a pKa prediction challenge. The compounds involved are 24 kinase inhibitor-like fragments, so they're smaller molecules, and they have a number of pKa's, so 31 experimental pKa's. And they were given to a number of groups to see how well they predicted those ionizable sites. The second set there is a publication by Jensen, Schwein, and Olsen. They were looking at drug molecules, but drug molecules that were essentially basic. They had previously worked on acidic compounds and come up with good models for acids, but it was the amines, the basic molecules, that were having problems. Their particular methodology uses an isodesmic method. So again, computation of a pKa, but it had to be relative to a reference pKa. It had to have a known pKa to start with. So these are our 2 independent test sets. So if I take the sample 6 data set first of all, what I show on the right-hand side is predicted versus actual. Again, the line of equivalence with the tram lines of plus and minus 1 log unit. And in the table on the left-hand side, the top line, our model has a root mean squared error of 0.85, even better than the actual test sets that we had within the model building process. Within that table, I also list the publications and their root mean squared errors that they publish. And as you can see, we perform very well, almost equivalent to some highly computationally intensive ligand-free energy relationships that involve conformational sampling, DFT level calculations. Now, they are very accurate, they get it right, but it is expensive. It is a time feature. We can do this on a semi-empirical basis using AM1, and therefore we have a much greater speed advantage. But you can also see that our model is predicting for all compounds. There are a number of results there which say that the Bannon model, that's the second row, the RMSE doesn't look too good, but it is influenced quite heavily by one amide anion outlier. It reduces down. But we have no outliers. We do, unfortunately, mispredict a few compounds, and I have identified those compounds in the graph on the right-hand side. Just a few comments about these particular compounds. The one on the far left is actually the third pKa that is listed here. The other 2 pKa's lie well within those tram lines. So it is the third pKa which we have missed in this particular case. The compound in the bottom right, the acyl aminothiodiazole, this is an interesting compound in terms of you expect this particular NH group in the amide to be acidic. It is next door to the aromatic system, but we are given data that says this is the pKa. We're not given the data as to where it's the pKa or what is the pKa. And so one looks at this and thinks about, is this a tautomer problem? Is this an acidity? Is it the basicity that we have to predict? And I will come back to this point in terms of tautomers and certainty later on. The other 2 examples on the top of the graph, again, we don't necessarily know what the pKa value actually refers to in this particular case, but this particular compound does illustrate the potential for a conformational restriction. With these 2 ortho groups, you can have one group influencing another, and if you just so happen to pick an incorrect conformation or don't sample enough conformations to actually understand how things vary, then you may get, and I think in this particular case, it's the reason why we mispredict. And finally, the thiazolidinedione that's there is a little of an annoyance to me, because this particular compound, as the model has developed, has actually got worse in terms of prediction. If we had one of the earlier models, then we actually got this molecule a little bit right. But the prediction for this acidic center has been influenced by the development of the model itself. So the next, or the other data set, the Jensen, Swain, and Olsen, I've listed again our predicted versus actual results. This is a little bit complicated in the sense of these are drug molecules. These are things that people were really interested in, and so some of these compounds do actually occur in our training set. But I've quoted here the root mean squared error for all 53 pKa's, and it is below 1 log unit. However, if you exclude the few compounds that are actually in our training set, that root mean squared error really doesn't move that much. It flips the other side of that 1 log unit. And this level of performance is equivalent to that found by Jensen, Swain, and Olsen using solvent corrections. Again, it's a PM3 or AM1 semi-empirical methodology that they've used. But again, I put in bold there, it is only that sort of performance level after removing the zwitterion heterodoxal. We don't have to do that. We've predicted for all of these compounds. However, the outliers that I note on the right-hand side, again, give some sort of indications as to what are the performance quirks of this model. The first one, the amidine in the left here, you can see that a number of things that we mispredict, we are mispredicting on the more acidic side. We are under-predicting the pKa for these molecules. And I think with the amidines, it's because we actually have very few acyclic amidine substructures within our data set. We have a lot of aminopyridines, aminopyrimidines that contain that substructure, but they are cyclic. And I think in this particular case, we have a paucity of these acyclic amidines, which is something I would want to correct. But then we'd also have to consider what possible conformations for this system what it could undertake. Spartine, the molecule on the right-hand side, this diamine structure is really interesting to me because it is perfectly set up, as you can see in the ball and stick model, to have those nitrogens share the load. They bind that proton in a really nice caged configuration, really nice and stable. Unfortunately, our model is based on the premise that this popularity contest that is going between compound and solvent, and that is the thing that weakens the interaction between the hydrogen and the compound because it's competing with the solvent. In Spartine case, it's not the solvent that's competing with the positioning of the hydrogen on one nitrogen, it is the compound itself. And therefore that I think is why we have a prediction which is more acidic, because we look at this system and say, there is something that is elongating that NH bond. It doesn't seem to be, there is something else that is pulling that hydrogen away. And we make the assumption or the inherent bias within the model that that is solvent. Unfortunately, that's not the case. The only way that we can make improvements with this is to actually bring in more conformational sampling. We have to bring in some sort of form of being able to estimate the intramolecular stabilizations of charged species to be able to parameterize those descriptors and understand when this might occur. But that brings its own issues. For conformational sampling, we only consider one conformer, and that is also in the prediction as it is in the training of the model. We could go to conformational sampling, but that extends the calculation time, and one has to then think about how one takes the contributions of each of these different conformations and their energies, and then I think this just overcomplicates the system. What we also need to do is think about carbon acidities. I mentioned at the beginning that we deal with X atom being nitrogen, oxygen, or sulfur. And we have missed out all of the carbon acids, so those CH groups that are flanked by electronegative conjugated systems, making that acidic. If you import and try and predict for that molecule with the hydrogen on the carbon, we will not make a prediction. However, for most of these carbon acids, there tends to be a way that you can make the other tautomer, remove that hydrogen, move the electrons around such that the hydrogen actually exists on a heteroatom. And in that particular case, we will be able to make a prediction. And the final thing, it refers back to that acyl aminothiodiazole that we have. I have said that our model is built on our knowledge of where a particular hydrogen sits and our ability to say this is the atom that is losing the hydrogen. I've also mentioned that we have a lot of 2-aminopyridines in there. We have some guanidines. We also have dialkylpiperazines. And you can say that a pKa exists for a piperazine. You know it's that group, but of course you're not really saying that the hydrogen is on this particular nitrogen of piperazine or the other nitrogen of the piperazine. So there is some doubt and ambiguity. And what we are calculating, although we put it out as a macroscopic pKa, are really microscopic in these essences of slight uncertainties as to where a particular hydrogen will sit. With things like the piperazines, it's going to be a combination within solution. There are going to be times when the proton is on one nitrogen and times when it's on another. But we have had to take that whole data point and just assign to a particular nitrogen. So all of these things are things that we are considering for future improvements into the model. Just in summary, what I'd like to emphasize is that we now have a single model combining whole molecule quantum mechanics, this is AM1, with QSAR machine learning in the radial basis functions to produce a model with a predictive accuracy of under 1 log unit. This model has comparative performance to higher level calculations as DFT in the sample 6 set and solvent correction semi-empirical models out of the Jensen, Swain, Olsen test set. The performance of this model is very good. However, we would love it to be performed on the molecules that you have within your set. Finally, I'd like to acknowledge the help and cooperation of the development team here at Optibrium. Thomas and Coran have taken this model and done the integration with Stardrop and the presentation of Stardrop, which you will see in a few moments. Layla was our sandwich student who originally started this project a couple of years ago. And I am very grateful to Jeffrey and David at LASA, who were instrumental in expanding the data set that we have quite greatly and enabled us to produce the models that we have. So thank you very much indeed. And I will now hand you back over to Nick.
Thank you very much, Peter, for a really interesting talk, and great to hear a chemistry joke sneaked in there at some point. So just as a quick reminder before we hand over to Tamsin, if you would like to ask Peter a question about any of the technology or application of using pKa, please use the GoToWebinar control panel. So at this point, we'll just pause a second and we'll hand over control to Tamsin, who's going to actually demonstrate what these models actually look like within the Stardrop interface.
Hi, thanks very much, Nick. I hope you can see my screen. So I'm going to show today how the pKa models are presented within Stardrop and how they can be used to analyze your project data. I want to start off with a data set I've got which contains 4 diverse compounds. Prosulfuron here is an agrochemical. Haloperidol is an antipsychotic drug. Of course, we're all very familiar with ibuprofen, the painkiller, and clinofloxacin is an antibacterial compound. And these compounds, these 3 came from PubChem, and this data came from the AstraZeneca deposited data in Campbell. Now, I'm showing here on the left-hand side the Models tab in Stardrop 6.6. This is slightly different from prior versions in that we've separated out the new pKa models. They're a little bit more compute intensive from our original ADME QSAR models. The StarDrop ADME QSAR models run on the data set as a whole, whereas for these more intensive models, it's necessary to select the individual compounds which you would like to run the data set on. So I can select a couple of these compounds, and then I can set it to run, choosing either only to run the calculation for the most acidic pKa, the most basic pKa, or to obtain them all. I'm going to run all of these. This will output 3 columns for me in my data set. And as you can see, ibuprofen is running at the moment. And instead of waiting for this to finish running, this can take a little while for each compound. I've got a data set that I prepared earlier in which I've run the data for all 4 of these compounds so that we can look at the results. So first of all, we can see the results for the most acidic and the most basic pKa's, and compare those with the published data. In this case, we're getting a very good reproduction of the measured pKa's for all of these compounds, especially when, as with all of our StarDrop models, we do output the confidence that we have in each of these measurements. And you can see in the bottom row, we're able to calculate both of the reported pKa's. In addition to this, we also provide an image that shows all of the available pKa's in this molecule. And what I'd like to point out is that in this case, the basic pKa's labeled B2, you can see that there's 2 of those in this molecule. They are calculated in the presence of the already protonated molecule at position B1. So how can I use this information? Well, perhaps I want to put this into a PowerPoint slide for my project meeting. I can select some of the rows here. So perhaps I want to select the structure, the different pKa's, and the name of the compound. And I'll select all 4 compounds in this data set, and I can push that out to PowerPoint. This will open up a PowerPoint presentation for me and produce this nicely pivoted table, which gives me not only the most acidic and the most basic pKa, but all of those individual pKa's as well. Now, if the image was important for me, I can copy and paste any of these images directly into other presentations and reports. Now, how else could we use this data to supplement the data analysis that's in StarDrop for working with our project data? So I have a project here where I've got some serotonin reuptake inhibitors, and I'm interested in trying to design some new compounds that might have an improved activity for these for this assay, the serotonin transporter log Ki, but maintain a balance of ADME properties. So I've developed a scoring profile that describes the outcome that I'm looking for my project. And in this case, we can see that these 3 compounds, they're all not very active, but they have this balance of the different ADME properties. I can use StarDrop's idea generation and using transformations to design some new compounds that I might be interested in further evaluating. And in this case, I've designed a data set of 63 compounds in which I've scored all of the compounds for this balance of properties, and the data set is ranked with the highest scoring compounds at the top. But I'm also interested in the basicity of the nitrogen here. We know that this pKa is important, and so I can modify the scoring profile to include that pKa measurement for the most basic pKa. And I want to show you here, let's go to this particular data set. So I wanted to show the distribution of the pKa's in this data set, which of course I haven't calculated. So in fact, I have another data set where I have gone ahead and calculated the pKa's for these compounds. And so now if we look, we can see the distribution of pKa's across the 63 compounds. And this is the desirability function where I'm focusing on compounds that are fairly basic, but not too basic. And so I can start to score these compounds, adding that basicity into the scoring profile. So the scoring is carried out very quickly. And what we can see now is that if we start to look down, if you remember, these were ranked according to the original scoring profile. But now if we look down these high scoring compounds, what we can see is the fourth one actually has this nicer balance of properties. And so this one might be more interesting than some of these other compounds. And we can then go on to use Stardrop's design capabilities to design some changes. Perhaps I'll try making this the dimethyl analog, and I can add that to my data set. And if I go back to the models tab, I can go ahead and start to calculate the pKa for that new compound. So that's what I wanted to show you, how we can make these calculations. We can use the information in our analysis of the data to incorporate into scoring functions when considering the multi-parameter optimization, identifying those compounds with an appropriate balance of properties, and also how we can present the data to our colleagues, for example, in a PowerPoint presentation for a project meeting. So at this point, what I want to do is hand back to Nick and Peter.
Thanks very much, Tamsin. So thank you very much, everybody. You've been very busy during the demonstration with questions. And so what we're going to do now is go to those. So the very first one that came in about 2 minutes into the presentation, actually, was, would you ever think about adding the temperature and pH at physiological conditions?
Essentially, that is the basic criteria that we have for collating the data set. So again, we have been looking at those pKa's which are recorded, I'd have to say room temperature. If the question is more about 37 degrees, then obviously that's going to be slightly higher. We're certainly interested in having a comparable data set. So if the data that is reported with those conditions, and unfortunately not all literature data is reported with those conditions, then we can certainly think about collating a data set at that particular set of conditions. I mean, the physiological as well would be something with respect to ionic strength. Not only temperature, but ionic strength affects pKa's. So again, if one had a particular view and a particular ionic strength in mind, then we would be open to looking for that data.
Thanks very much, Peter. Second question is, how does your method treat tautomers? Does the model predict tautomer ratios? Would different input tautomer structures lead to different pKa predictions?
To answer the final part of that first, yes, it does. It does matter indeed. Because we are dealing with the conjugate acid and the conjugate base, we are dealing with the location of the proton and the atom in which it is connected. If you connect it, as I mentioned, via a carbon, it's going to have different properties in its neighboring surroundings than if you connect it to the oxygen or nitrogen that may well be conjugated to it that's making that CH bond acidic. And so our general philosophy within StarDrop is that you know your compounds best. So if you have a particular idea that a tautomer is the correct one in the aqueous environment, then that is the one that we would expect you to make a prediction on. I have to say, with carbon acids, we are somewhat forcing you at the moment to have the tautomer where that hydrogen is on a heteroatom, but this is something that we will be developing in future as we can bring in carbon acids into the extension of the model.
Thanks, Peter. Next one is, where is our experimental data coming from that we used to build the model? Is it public domain data, for example? And was it measured by us? Certainly not in this particular case. And are the compounds chemically diverse?
I would say that they are chemically diverse. The literature is publicly available. We are going to present this work in paper form where we will have the references from which we abstracted that information. Although the compounds themselves, not all of the references, we will include the compounds that are included in our various sets, and searches of the literature will be able to find those data points. Have I answered all of those?
It would, yeah, I think so, yes, yeah.
Right.
So next one is, what type of charge do you use, and did you do benchmarking of this?
Well, I'd have to say these are essentially Mulliken population charges out of the AM1 optimization. No, I did not choose different charging schemes. I didn't go to RESP-fit charges or any other particular way of estimating an atom-centered charge. So,
for multiprotic molecules, does this model predict macroscopic pKa values or microscopic pKa values?
I'd have to say that these are more likely to be considered microscopic. We are comparing, unfortunately, to a macroscopic value. But because we are concentrating on a particular atom and its ability to have a hydrogen or lose a hydrogen, then you are looking at a particular estimate which is for that site, and one can really be considered microscopic. Because our data is macroscopic, because our data sets are monoprotic mainly, or with diprotic in there as well, we are pretty confident that a pKa is for that site. If you are looking at molecules that have more than 2 ionizable sites in there, then that is getting towards the extremity of our particular domains of our model, and it is likely that the errors, as we identified in one of the in the sample 6 data set, if you're looking at 3rd and 4th pKa values, then we are likely to be less accurate on those. So.
Thanks, Peter. The next question, I think, probably relates to our StarDrop ADME QSAR models and asks how reliable is the distribution and blood-brain barrier prediction. I think, the same principles that Peter described earlier around taking a great deal of care in terms of curating data sets is used in all the models that we deploy through StarDrop. And obviously, with any in silico model, the accuracy of our models will depend on the similarity of the compounds you're working on to those that we've used to build our models. And so, as Tamsin demonstrated, with all of our models, we also calculate an error associated with that model, which reflects the domain of applicability. And so, to answer your question, you would be able to determine the accuracy of our models by looking at that error by applying our models to your compounds. The next question relates to AM1, and is the AM1 quantum mechanical computation engine included with the new pKa module, and is this now part of StarDrop 6.6?
Yes, we have to run MOPAC calculations to generate the QM descriptors, which are then fed into the model to make the predictions. This is an engine that is associated with the model. It's not a separate engine, so we're not selling this as a way of doing semi-empirical AM1 calculations. It is an engine that is specifically there to generate the descriptors, which we can then enter into the model.
Thanks, Peter. Can you see a distribution of species plot within the StarDrop interface?
Not currently, no. And this is something that we have heard before in terms of user requests. Having got a pKa model, then this is the next request on the list, and certainly it's something that we will be looking at trying to implement. Generally, I would say that if you happen to be able to see the pKa values that are associated with the particular ionizable sites, then one should be able to have a good idea as to what the charge distributions are likely to be, what the sorts of percentages and occurrences of particular charges at particular sites, reference to, in our case, pH 7, 7.4. So I think, as we noticed in that bimodal distribution, there are a lot of pKa's that are well separated from 7. And so if you are in that particular domain, then seeing that pKa will sort of say, in water, this is going to be charged 100% of the time.
There are two questions that have come in that are sort of related to each other. One is, which algorithm do you use in the back end? And the second is, can you explain briefly the RBF methods that we use? So obviously the algorithm that we're using is a radial basis function. So we'll probably try and keep this short because Peter could probably give a whole new webinar on the modeling approaches.
I'm not actually sure how much level of detail is required in there. Radial basis functions is a nonlinear function which is trying to produce a function that describes each individual molecule in the training set, which is one of the reasons why I didn't put the training set points up on the graph, because they are by design all going to lie very, very close to the line of identity, because the functions that are generated in RBF are going to try and explain those particular molecules. RBF methodology has been used quite a lot in neural network training and in image compression techniques, but it's actually not all that common in QSAR methodologies. I'd have to say it's very good when you have a large number of data points, as in the couple of thousands that we have here, and it is very good at interpolation. Extrapolation from that particular set gets a little bit more difficult with RBF compared to certainly the Gaussian processes that we have. They are much better at extrapolation outside of the data set. But considering the data set pKa range that we have is in about the -2 to 14 range, that's the sort of range that we feel covers the majority of occasions that people will be facing. If we're going to the carbon acids or if we're going to the alkyl sulfonamides, these are going to extend that pKa range, and therefore this is something that we would have to build into a new model. But hopefully that gives a very brief description of what we have in our particular techniques. But if anyone has any needs more detail, then I'm more than happy to provide it offline.
We've got two questions that sort of relate to the application within Stardrop, and one is how much time would be required to calculate the pKa of a molecule that has two sites of ionization, and can we also actually predict the overall pK of a drug molecule as a single value?
The time frame, the times that I have for the training set and the validation set and the test sets that we used in developing the model, it averages out for about 17 to 20 seconds a molecule. Now, these particular molecules have quite small, more rigid structures and are monoprotic, but they do go up to much larger molecules in the many hundreds of molecular weight, flexibility, and obviously two sites. And in this, it is going to take longer. So the time taken for a particular molecule will depend upon its flexibility and the number of sites. If it has two sites and, should we say, under about 8 rotatable bonds, then I would expect it to be done well under a minute.
Okay, can you calculate the isoelectric point of compounds with several ionizable groups?
No, that's not necessarily something that we have been looking at. Again, we've been looking at the individual predictions for each individual site.
Okay, so there's quite a specific one here. Why not say sulfonamides?
Yeah. Essentially, the reason why we haven't, I haven't put in carbon acids in terms of benzylic CH acidities or sulfonamide NH acidities is because this would extend the pKa range quite dramatically. And if you're dealing with a pKa range that goes from -2 to +40, then your statistics are going to look excellent, whatever you manage to do. But for the most part, as I said, one's interested in pKa ranges that are around between the 2 to 12. And if you are extending the pKa's that you're modeling to these much greater values, then you're going to lose some of the nice discrimination and information that you get in these lower ranges. I have to say, it's not all sulfonamides. We do, as Tamsin demonstrated, work with acyl sulfonamides and those that we know are going to likely to be acidic. These are acidic mimetics in there. Amides where the nitrogen is connected to an aromatic system or has some conjugation, those are going to be predicted because, again, we look at those as having the potential to be acidic. But plain alkyl sulfonamides, alkyl amides, the pKa's for these molecules are in the extreme range and not necessarily something that we think that within water you're going to have any sort of concern as to whether it's ionized or not.
Thanks, Peter. We are coming towards the end of our time here. So one final question before we close today's session is, do you optimize many conformers and pick the most stable one? If yes, how many?
No, it's just a single conformation. So this is why we are looking at some of the mispredictions may well be due to the fact that we are not necessarily sampling many conformations and picking up some of the nuances which actually alter the pKa's. We do this because of speed and because we're dealing with AM1. Again, that's a speed concern, but trying to keep some sort of relevance and some sort of ability to estimate the electronic distributions and make these things a little bit more accurate. So no, we only do one confirmation, and that may well be something that could improve the stats of the model.
Superb. Thank you very much, Peter, for the really sort of detailed answers for so many questions that have come in today. So with that, we'd like to end today's session. For those of you that would like more information about these models, or if you'd like to get hands on this, then as John mentioned right at the very beginning, StarDrop 6.6 was released today. And if you're an existing user of StarDrop, then the pKa model is included in the ADME QSAR module. All you need to do is update to the latest version and you'll have access to those models. If you're not a user or you don't have access to the module, then please feel free to get in touch with us and we'll be happy to make that available for you to try out. There are a number of other features in StarDrop 6.6, including a very extended suite now of CSAR modules to really sort of take you through all of the steps of structure-based design. And with that in mind, we will be having a new webinar within a week or so, where we will be demonstrating some of this new functionality and again answering any questions that you might have. And with that, I'd like to thank you and thank you very much for joining, and we look forward to seeing you at our next webinar.